Hi, this is Prasad. This is my presentation on LISA, a learned index structure for spatial data, and authored by Fengfei Li et al., published in SIGMOD in 2020. So the summary of the paper is like LISA replaces traditional spatial indexes like R-trees with learned machine learning models, maps spatial points to one dimension, and predicts shards which are ranges in one dimension, and stores them using local models. So faster range and k-nearness neighbor queries, and takes less storage and efficient updates. The problem with traditional spatial indexes like R-trees are like they take large storage and high I/O and poor at handling updates. So the goal is to replace R-trees with machine learning powered spatial indexing. So the core idea is uh, the mapping of a raw data where we can see in a rectangle of each query, convert these positions xy into a one dimension z positions, and sharding like uh, making a range on this one dimension to predict shard ID from z using piecewise linear regression and given place data in pages. So the benefits are like replacing tree traversal with fast prediction, and indexing becomes machine learning guided layout. So the LISA's framework is like here in picture A, it is the raw data. So and we map this raw data by giving a grid cells partition, and mapping this function converts into one dimension, and we give a shard prediction model SP. So this SP model will try to model this raw data, and local models manages pages, and these pages use fast memory efficient layout for queries. So overall this framework is shown in this above diagram, like raw data converted into a grid, and the SP function is learning this grid data structure and giving into a page, converting into a pages and giving the shards. So how this range querying process will model this data. So the steps, as we mentioned here previously, maps query rectangle to Z intervals and predict shards to check ready only those pages. For example, here there is a position x0, x1 for a raw data, and we need to query this position into Z, and this position will convert into some value 10, 25, and given a short range. For this range is like S0, S1, something like that. So the advantages are like few pages reads than R3, like less than 10, 20%. So when we come to k-nearest neighbor querying process in this approach, so lattice regression predicts a radius R or delta. Uh, this These delta ranges will convert into a range query and filter exact k nearest points, and achieves uh, 0.32 milliseconds of CPU time. So these are faster than KD tree and R tree, whereas the R tree takes 1.05 milliseconds. And also the dynamic updates, it accommodates insertion, deletion. So the advantages are local operations and no global rebalancing. So the experimental results shows that upon performing using these real-time data like IMIS, ImageNet, and Uniform and ZIF, so the results seems to be 10 to 20% less I/O than R-trees, and smaller memory footprint and faster query responses even in high dimensions. So the performance here for ImageNet and 3D uniform data The Lisa performs a CPU time of 1.43 milliseconds and response of 10 milliseconds. Where for ImageNet it take 5 milliseconds CPU time, 5.08 milliseconds, and 27.22 milliseconds. We can observe it is more compared to ZM, uh, but overall this experiment shows that we can have a machine learning approach for querying uh, a real-time database. So the key takeaways are like Lisa is a machine learning powered index replacing R-tree and better performance, dynamic updates, and takes less memory, ideal for big and dynamic spatial data. So the future steps for this paper was like integrating a deep learning integration and support for spatial joints and trajectory data and smart partitioning for skew distributions. Reference of this paper. Uh, Thank you.